Brittany.
Okay. So the circuit shown on the image above consists of a U-shaped wire that's going from here, open ends on this side, coming around with a resistance of 20 ohms, with the ends of the connected by a sliding conducting rod. The magnetic field filling the area enclosed by the circuit is a constant 0.01 teslas, and notice the direction of the magnetic field. If the rod is pulled to the right at a speed of 1/2 meter per second, what current is induced? So what's going on that would create a current?
Like, there's magnetism. Wait. Magnetic field filled an area enclosed will induce like the flow of electrons, like something's being pushed because it's being pushed, because the rod is being pushed to the right, and therefore there's going to be a pushing of electrons.
Okay, because we can say emotional EMF.
Yeah.
Or we can go to Lenz's law.
Okay.
Or not Lenz's law, Faraday's law of induction. Faraday's law of induction is the straightforward way of doing this. The induced EMF is equal to minus, I'll put the N here, and it's just 1, change in magnetic flux over change in time.
Okay. Yeah, because we have time. I figured it would be something along that line. And then do we have to find the flux?
Yes, we do. So what's the equation for the magnetic flux?
The emissivity, no?
Much simpler.
So it's just...
we talked about this earlier today when we did Faraday's law of induction.
Yeah, I thought it had the emissivity. It's like area...
That was in our calculation of magnetic field.
Area times the magnetic field.
Yes, it's the area parallel to the magnetic field. So B dot A. Now in this direction, the magnetic field is coming out, the area is coming out, so it's just B times A.
Magnetic, wait.
Right, the magnetic field has a circle with the dots, that means it's coming out.
Yeah.
And the area is normal to the surface, so coming out. So the magnetic flux is just B times A. Okay. What's the equation for the area? Just using your finger, where is the area of our loop?
I don't know where close is. It says it's a U shape. So we're here?
Our loop is connected by the sliding conductor. So the area is this area here. Now, of course, I'm not doing a very accurate job on the edges, but...
You don't need to be an artist.
I could ever be an artist. Okay, so there we can see there's the area.
Yeah.
So what's the equation for the area of, obviously, what's the name of the shape that I just did? Well, rectangle.
Rectangle.
What's the equation for the area of a rectangle?
I'm not sure.
Area is length times width.
Oh, okay.
So what's the length of this? It's just given as L, right? What's the width?
It would be like W minus V? No.
I put a W0 for the initial width plus, because the areas can be getting bigger with time because the direction's going. And then V multiplied by? How do I get the distance from?
By L?
No. V times T will give me the distance it's traveled.
Because that makes it a function, right?
Well, yes, but more importantly, distance traveled is equal to speed multiplied by time. Average speed multiplied by time, but it's constant speed. So
okay.
So that's my equation for area. So now if I do the change in magnetic flux with time, well, you've taken calculus. That's really the derivative.
Mm-hmm.
So I'm really taking that derivative. BL and W0 and V are all constants. So what's the derivative of that?
0.
Not 0.
Right.
Time is not a constant.
Time.
Well,
Like times. Okay, so BL and V are all constants, right?
yeah.
So you'll have like how how the, what do you call it, angular velocity?
It's actually W, not angular velocity.
Okay. W, no. You're like how 2W
I'm gonna write this in the most
times 2.
That's the most clear way it can be written out. What's the derivative of 1?
0.
Yeah. So this is equal to 0 plus BLV. What's the derivative of time with respect to time?
1.
Okay. So I just leave 0 plus BLV. So that's what we get for the derivative of the flux with respect to time.
Okay.
Our n is just 1. So our EMF, what's the minus sign mean?
The direction.
It means we need to check the direction with Lenz's law. So we have the EMF.
Mm-hmm.
We can do the current because it asks for the current. What is the current? Is equal to the EMF over R equals BLV over R. And we can get the number for that. B is 0.01 Teslas. L is got to be given somewhere.
We're given the we're given the EMF or V, right?
No, we're given the speed. V.
Okay. Yeah, I need to be careful.
I don't see L.
Where's the EMF?
The EMF we calculated.
Okay. Because we did the magnetic flux, we were given that.
We're given the magnetic field.
Okay, we're given the magnetic field constant T for Teslas, right? That's a Tesla?
Yes.
Okay. And then times the area. So we did that. And then we have resistance. Do we have? Yeah, we have the resistance. Yeah. So wouldn't we just do that instead of the L?
No, this time I'm not overlooking anything.
Just because if it all means the same thing?
You have to have this distance. And it's not given.
Can we solve?
We cannot.
Okay.
That's crazy. I mean, how do you not have that distance there? So what we're going to have is, 0.5 times 0.01 is 0.005 divided by 20.
Do you want me to calculate that?
Sure.
Okay. Divided by, okay, so we have 4.25 times 10 to the negative 4th. Yeah.
Something went wrong there. It's got to be 2.5 because the top is 5 times 10 to the minus 3 divided by 20. That's a Tesla. This here is not a number, that's Tesla's.
Oh. Okay, so yeah, now I have what you have.
Except for it's -4.
Mm-hmm.
Yeah. Okay, so we have this here, but we have to know the length to actually get the value. Second part, what's the direction of the current?
Okay, so the velocity, which is these fingers, no? My thumb is what I want.
Go to Lenz's law.
Chapter 22, maybe. You would think that. Lenz's law. Where would I find that? Do you know? Which chapter?
23, I believe. Yeah.
Oh.
Faraday's law and Lenz's law.
Okay, so Faraday's law of induction. Yep, I understand that. Okay, Lenz's law. Manifestation of the conservation of energy. How is it? Okay, Faraday's law. What is Lenz's law? What's the difference?
The difference in Faraday's law and Lenz's law?
Yeah.
Lenz's law is the one that gives us the direction.
Okay, the minus sign in Faraday's law signifying that the EMF induced in a coil opposes the change in magnetic flux. Okay.
So what's happening to the magnetic flux as this rod moves? Increasing. So Lenz's law says it's going to have an induced current that would oppose that increase. So what direction would the induced current have to flow if it's going to oppose that?
Opposite.
Okay. You said opposite. The magnetic field is going to be opposite. Which direction is opposite for the magnetic field to be opposite? What direction is the magnetic field pointing? In this picture, what direction is it pointing?
Out of the page.
Okay, so what direction is opposite to out of the page?
Into the page.
Okay, so if I'm going to have a current that makes a magnetic field that goes into the page in the middle of the loop, what direction does the current have to flow in that loop?
So you want into the page.
So what direction are your fingers wrapping? Clockwise or counterclockwise?
Clockwise.
Okay, so we're going to have a clockwise current.
Okay.
So that's as far as we can go here because we don't have that length. Now watch, we'll look and see that there's somewhere where it has the length hidden that we don't. Nope, it doesn't have the length anywhere. And their answers are based on, well, they have the number that I came up with, 2.5 times 10 to the minus 5.
So they didn't even mess with the length.
So yeah, they didn't. Look at your calculator again.
Yes.
Okay, so we have 0.01 times 0.5 divided by 20. Yeah, you did it right. So they must have assumed that it was 10 centimeters long, but there is no place that says it's 10 centimeters long.
Weird.
Or if there is, my reading comprehension is lower than even I thought.
Please don't do that on the test.
I try not to. Okay, electric generator. Okay, this one has 3 questions.
Okay.
4 questions. Wow. Yeah. Oh, bad. Where's the peak? At what time?
So something with frequency?
Well, the last one has to do with frequency.
Gives me a good direction. So I think is this an AC circuit or peak EMF? Okay. I feel like if I didn't have this app, I wouldn't be as familiar with the sections. Okay. So, does this have to do with like inductance? What are we given?
Haven't even read the problem yet.
I did a couple problems in the homework, like by myself, without like asking for any like help or anything, and I didn't have to even like ask for a hint on the expert TA, and I felt really
good. Okay, so now we can read the problem.
Yeah.
A 75 turn, 10 centimeter diameter coil rotates at an angular velocity. So we're going to say that we have a coil here. So here's my axis of rotation. And it has diameters equal to 10.0 centimeters. And it has N equals 75 turns. And it has angular velocity. Omega is 8.00 radians per second. And we have finally...
Wait, do we have a current?
A magnetic field. And I'll just make the magnetic field go vertical. .25 Tesla.
Okay, so EMF equals...
starting with the plane parallel. So that means it's starting with the magnetic field. Well, if I'd shown it like this, I would be correct.
Okay, so EMF equals the negative N times the delta flux, the change in flux, or the change in time. Are we given time? No. So I need a different equation. I'll keep looking. There's also... I'll keep looking. Not the one. Yeah, this is a solenoid. We have... What about... would we use... No, because we have... Do we have time?
Well, we are going to use theta is equal to theta initial plus omega t.
Okay. We went over that last class period, yeah?
I believe so. So, first of all, let's start with a simple question. Why is this going, it asks us, what's the peak EMF? Why would it be producing an EMF?
EMF is just like velocity, right?
No, EMF is voltage.
Yeah, this is bad. Okay. It would be producing a voltage because we would have a force. We have... Because alternating? An alternating force? We have an angular velocity.
We have changing magnetic flux.
Mm-hmm.
And the changing magnetic flux, according to Lenz's law, will create an EMF. We can actually look at this, because you've taken calculus, we can say, what is the flux?
Mm-hmm.
The magnetic flux is equal to, of course, B dot A is equal to the external magnetic field times the area. So they gave us diameter, so I'll put pi diameter over 2 quantity squared. That's radius. So that's B times area, but then it's going to change with angle. And so at time equals 0, it tells us that the magnetic field is in the plane of the coil. So the flux is 0 initially. And so that would be times, and I will put cosine of theta equals B pi d over 2 squared. Well, I don't need to use that anymore. I can put d squared over 4 cosine of theta initial plus omega t.
Mm-hmm.
So that's the magnetic flux.
Mm-hmm.
And so the induced EMF is equal to minus n derivative of magnetic flux with respect to time equals minus n. And then I have b pi d squared over 4. Those are all constants. What's derivative of cosine?
Sine.
Derivative of cosine is minus sine.
Minus sine.
Is that right?
Yeah, I think so.
Yeah, derivative of sine is cosine. Yeah. And you have to use the chain rule, which is going to bring out an omega.
Yeah, I'm going to go to my other office, so. Okay, thank you. Oh, you're on, Ryan. See ya.
Some of this does make more sense with calculus. Like, whenever, like, for the last test, when you understand that, like, oh gosh, there's like a couple equations that were just integrals of each other. It's really helpful to understand the.
So here's our equation for the EMF at any time.
Okay.
And so what's the maximum that it's going to give you?
Twice that? Or squared?
What's the maximum value? Okay, this all here is constant, right?
Mm-hmm.
And what's the maximum value that sine will give you?
9. No?
That's the angle at which it gives you maximum.
Yeah. 1. Sine of 90 is 1.
So that means our maximum is going to be omega times n times b times pi d squared over 4.
Okay.
That's our maximum. What's our minimum?
I don't know. Minimum would be 0 or like.
The minimum would be minus that.
Okay.
It's going to go between plus that.
Oh,
and minus
because
that.
I forget that we're looking at like a frequency, or I feel like if I drew it out.
Okay, now the second part here, if I did my angles right, that is, if my theta aught is 0, or excuse me, is 90 degrees, then when do I have my first peak? So I'm going to start at time equals 0 at sine of 90 degrees.
1.
Sine of 90 is 1, so I'm going to have my first peak at time 0 if I identified the starting angle correctly. I always have to think about these things again and again and again. But I'm pretty sure I did this flux right. B dot A, right? It's a magnetic field times the area. And we're starting with the area and the magnetic field 90 degrees from each other. And so dot product is parallel parts, so that's cosine of 90 degrees plus omega t. Or it could be minus 90 degrees plus omega t. You don't know which way it is. In terms of what direction is the magnetic field pointing? Is it pointing this direction or this direction? You don't know. So I think I'm right there that this is going to be time equals 0 is when we have the first peak. The peak's going to be right at the beginning. At what time is EMF first at its most negative? Well, its most negative is going to be 90 degrees later, right?
Yeah.
And so time is equal to 9 degrees. I said 9 degrees. 180 degrees too.
Okay.
Right, 90 plus 180 goes the other way. So it'd be 180 degrees. So it's going to be omega t is equal to pi.
Mm-hmm.
So omega t is pi. It's pi over omega. And they gave us omega, so it'd be pi over 8. So pi over 8, whatever that is.
How do you know when it's just like last time it was just W, but this is omega? Like,
because this is talking about angular velocity. I know my handwriting doesn't look very different.
okay.
And what's the period? What's
the frequency? I remember this. It's in the last. Oh, okay. I passed it. I think it's this.
Well, no. This is something we learned last semester.
Oh.
We learned that period is 1 over frequency.
Yeah, frequency is.
And since omega, let me change colors here before I start doing stuff. Since omega is equal to 2 pi f, it's equal to 2 pi over period, then period is equal to 2 pi over omega. And so, we can put in numbers here. It was 0.01, right? Oh, 1.25, wow. 25 times 0. So what's 8 times 75 times 1.25? Well, 8 divided by 4 is 2. So let's just do the 8 divided by 4 in our heads and have 2 times 7, which is 14, or 75. 2 times 75 is 150. 150 times 0.1 is 15. Oh, 0.1 squared. So that'd be 1.5 times 1.25. Times pi. Now, did we do that right? Because, most of the math we did in the head. Yay! And then we got the next one was 0. So my interpretation definitely was right there. And so pi divided by 8. Oops. And then this was 2 pi over 8, so just times 2.
0.78.
Hey, by chance, did you get my lab book?
I'm not sure. I have my backpack. All my stuff is in the study, or if you want to check if I have 2, that's fine.
Okay, thanks. Because I was like, I know I had it with me last night.
Maybe.